Okay, so what's the big dilemma here? We developed this nice theory of relativity. It helps to bridge the gap between different perspectives and gives us this universal, absolute conception of the universe. What could possibly go wrong? My question for you is, invariance tells us that physical laws should be universal across reference frames. They should always crop up in the same manner regardless of our perspectives, regardless of how we perceive the event transpiring in front of our eyes. But we've only taken a look at Newtonian laws, Newtonian mechanics, F equals ma, and all the results that fall out because of that. Basically, inertial ideas. So, what about a theory that was developed after this? E&M, electricity and magnetism. What about that? If our physical laws were good, if the theory was very universal, absolute, we would expect that Maxwell's equations, which govern all of E&M, and we've shown, give us valid results through numerous experiments, people were very confident that those laws should be invariant between reference frames. What I'm going to say is, there's a little dilemma. And this is what gave rise to a lot of the questions in the late 1800s and early 1900s, which Einstein resolved with his theory of special relativity. What was the issue? Now, as I've just said, you would have hoped that E&M, the physical laws, would be invariant to reference frames, and that they would conform to this theory of relativity we just put together. And furthermore, since E&M was newer, people clung to this theory of relativity, this Newtonian result, because it had been proven time and time again. It could not be wrong. But here's the problem. Maxwell's equations assert that the speed of light, the speed in which light moves, is always constant. Why is that? Because he asserts that the speed of light c is equal to 1 over the square root of these constants epsilon naught, mu naught. Epsilon naught is the permittivity of vacuum, while mu naught is the permeability of vacuum. So, can you see the problem here? This is a constant regardless of what you want to say. But if this is a constant, if somebody in a moving reference frame shoots out a beam of light, this guy, it says that the guy who's not moving will measure a different velocity. But it's supposed to be constant. What is going on here? This was so troubling at the time, and I'll illustrate it with a new example right here just shortly, but this was so troubling at the time that scientists started coming up with fabricated ideas and theories and entities to try to explain this. But at the time, they respected this theory because it was Newtonian, it was classical. It had more supporting evidence, or so they thought. So what they said is, this law cannot be invariant across reference frames. What we're going to say is that there's some unique frame in which the speed of light is a constant defined by Maxwell's equations, and Maxwell's equations hold. But in other reference frames, it may be different to account for this theory, and that's how they bridged the gap. What they said was that, hey, look, light is a wave, and from our previous experience, we've observed that a lot of waves, such as water waves in water and sound waves in air, they have to propagate through a medium. So guess what? Light is going to do the same thing. It must do the same thing. So there must be this unique entity, which we're going to call the luminescence ether, or ether for short. This is going to be some medium, which is heavenly, given the name ether, some divine fabricated force that we came up with in our minds. And light is going to have to propagate through that. And only in that reference frame does this hold. Only in that reference frame do Maxwell's equations come rise, hold up at play. So, this was a problem. And what scientists wanted to do is They wanted to come up with an experiment with a tool that could precisely measure light, super precisely, in such a way that they could find some difference in the velocity in different reference frames. So they said, okay, let's take the Earth. The Earth is moving at a speed. We know the speed. We can predict that. From Kepler's laws, from orbital mechanics, we are confident in that result. Let's put together a tool that could measure it on the Earth. And what we assert is that in the ether, which surrounds the Earth, the light must propagate through, it's going to be this value. It's going to be 3.00 times 10 to the 8th meters per second. It's a very precise measurement. But on the Earth, it's going to be different. It's going to be different. So, a guy named Mickelson, who was also, or later assisted by a guy named Morley, and they did an experiment, which became known as the Mickelson-Morley experiment. They developed what is known as an interferometer, and Mickelson in 1880, what he did was he tried to measure the speed of light, and he thought it would give a different value than this because the Earth was moving. Right? We were in a different reference frame. So in essence, he was trying to find this guy. What did he find? His instrument was super precise, and he should have found a difference. But regardless of where he did it, regardless of how he did it, regardless of the time of day he did it, he always got that result. When he published this, scientists blew up. They're like, what? No! Our theories! This cannot be right. You did not do your experiment correctly. Do it again. He kept repeating it and finding that this was true. So, they had the answer right in front of them. But they came up with this fabricated idea to explain it. This fabricated conception. And the greatest lesson you can get out of this history lesson, is that physics is intended to observe physical phenomenon and then develop theories which describe what you see. As soon as you start prescribing how nature should behave, you get led down the wrong path. And that's what happened in this situation, because they had the answer right here, that these laws are invariant in any kind of reference frame, but they refused to believe it because they are trying to mold nature and come up with these ideas, these fictional entities, to make their theories work. Whenever you do that, you run into problems. Name of the game is observe. Develop theories to describe what you observe. That's how you do good science. Okay? So, what was the dilemma here? I'm going to illustrate it for you with Terence and Philip and another Gedanken, a thought experiment, as Einstein would say. So in this case, we have the same setup. We have Terence and Philip originally at the same origin. They calibrate their clocks. We think that the time is going to be the same. And this time, Terence and Philip are like, hey, let's pimp out this experiment, baby. I'm going to get a Star Wars ship, and I'm going to put a blaster on the front. Let's measure light instead of a baseball. That's child's play. And we got this nice theory here. We know what's going to happen already. So at time t equals 0, bam! Terence instantly goes a speed of 0.95 times the speed of light, super fast, almost close to the speed of light. And what he does, he says, I'm going to push a button, I'm going to fire this laser gun. It's like I'm in Star Wars, baby. It's going to be awesome. That's why he has this awesome, awkward smirk on his face. He pushes the button, and Philip is out in outer space. He's watching it, and he's writing down some theory based upon his new Galilean transformation. And he says, Terence, give me your measurement, and I'm going to be able to figure out what it should be before I measure it. I am so confident in my theories, I'm not even going to listen to what's going on right in front of me. So Terence hits the button, he measures The laser, pew, flies out. He says, oh, it's going a speed of C. It must be going through the ether. It's going through the ether. I found the ether, baby. We're going to make history. He calls up Philip. He's like, yo, it's C. And Philip's like, oh, I'm so excited. So excited. I'm going to figure out what I'm going to measure it as. Physics says it's going to be V. It should be V plus V relative. 0.95 plus C. It should be 1.95 C. He's super excited. He's holding it up. He's got his pen. This is what it is. As you can see with this big red line, that's not what it is. That's not what it is. In actuality, Philip measures the light. Let's see. What's going on here? What's going on here? Instantly, just like the scientists, they start saying, oh no, something is wrong with E&M. It's maybe we're not measuring it correctly. Let's do it again. Oh my God, They failed the lesson. They failed to realize that this is what we observed, so that's what it is. Trust nature, but verify. So what they found is that, yes, Maxwell's equations are invariant in the universe. And this was the main dilemma of the time. People could not understand why this theory was wrong. And then Einstein came around and he said, guys, it's right in front of us. It's right in front of us. You need to take your educated mind, your programmed mind, what you expect to see, and throw it in the garbage. Do not expect. Observe, develop, and then critique. Do not control reality. Nature will not conform to your wishes. It will not conform to your imagination. It will not conform to what you want. There is no ether. There is no special fabricated idea. Get out of here, guys. What I'm going to say is that our conception of space and time is not quite right. We haven't seen the full picture yet. And that is exactly what happened in his paper he published in 1905. What he asserted is that space-time is going to bend or change to compensate for this fact. But it's only going to arise in certain circumstances. In other words, we're going to observe that time dilates and length contracts. Two very important topics. Keep that in the back of your head. So, that was the main dilemma of the time. This is what perplexed scientists back in the day before Einstein came around, slapped them on the face and said, wake up, brother. The answer is right in front of you. Stop trying to force reality. Observe and then develop theories to explain what you observe. Nature is not trying to trick you. Nature will not trick you. Okay? So, the next few videos, we're going to jump into what Einstein asserted. He was able to resolve this nonsense, this big mess, through a very simple experiment, a Gedanken. Okay? And through that experiment, he was able to show how our conception of space-time is completely and utterly wrong, and he changed the fabric of physics as we knew it. But at the same time, he saved E&M in a sense. Made everything connect, came up with that universal absolute conception, and progressed with our theory of relativity. So I hope you enjoyed the video. A lot of background information, not a lot of math, not a lot of physics, but I thought it was important for you to understand the dilemma scientists face. Because it seems simple to us nowadays, but this perplexed everybody for years. And I wanted you to appreciate how a simple experiment, simple facts, can divulge so much about the universe. Okay? So I look forward to explaining the special theory of relativity next, going through Einstein's Gedanken, and showing you how time dilates and length contracts. Stay tuned.